Just to make sure we are all on the same page. Your homework 2 is due next week, so I've extended the due date. I've essentially given you 1 more week, but you're gonna have homework 3 due the same day. Is due next week, and it is I don't remember the date, but it should be sometime in February, right? Next Thursday, whatever. February 3rd. Okay, so 2/3, 2022. It is both of them. Your homework 2, I'm assuming most of you have gone over homework 2. I saw some of you were having some trouble with it. Did you fix the problem? Okay. And so I'm assuming all of you have started working on it, or at least have looked at it. And homework 3 is going to be I'm thinking of just an explanatory question. So I'm probably going to ask you to give me the angles that are important, like it, or different coordinate systems that we went over, just to make sure that you are all clear. And we had some issues with homework 1 grades. Your TA didn't put any comments down. I mean, she's not gonna put any comments on it. She's going to tell you what was wrong, right? She's going to tell you have lost this many points on this problem, right? And and she's going to start doing that from homework 2, right? At the end of the day, at the end of the semester, if it comes down to your homework 1 grade that you have lost, I mean, some of you have lost more points than what you really deserve to lose, right? So if it comes down to the homework 1 grade at the end of the semester, I'm going to go back and regrade the homework 1 for you. If you are, let's say you are at 89.1, right? And you need 1 point to get to A, right? I will go back and regrade the homework 1. Does it make sense? I think this is a fair thing to do, right? If you're not going to need the homework 1 grade, then if it's not going to affect your grade, then we are going to leave it as is. If it will affect your grade, then we'll come back to it. Okay, so with this all of the way, let's do a small recap, very small recap on what we did on Tuesday, because we are going to use this today. We had 4 different coordinate systems. First one was the Earth axis. What was the Earth axis coordinate system? On the surface of the Earth, right? X and Y, what was it? XG, YG are going to point on arbitrary locations on the surface of the Earth, and then Z is going to point downward. Z of G, I'm sorry. Next thing we had was the moving Earth axis. What was this one? So it is the same orientation as the Earth axis, but it's going to sit on the plane. X of E, Y of E, and Z of E. Next one was the body axis system. What was this one?
The axis where the X coordinate is drawn from the center of gravity to the tip of the nose of the plane.
Exactly. So X axis on this one passes through the center of coordinate, center of gravity, a line that connects the center of gravity to the nose of the plane. And Y of B and Z of B are going to perpendicular to that. And then we had the air path axis. Air path axis, what was this one?
It was the center of gravity of the plane to the direction, like
Exactly. So it is moving in the direction of the flight or movement of air, right? It is, the x-axis is parallel, y-axis is perpendicular, and z-axis is also perpendicular, right? And then we had a couple of angles that we dealt with. The first match of angles related to the was going to relate the body axis system to your moving earth axis system, right? What were those three or four? First one was angle of yaw or psi. And what was angle of yaw? Any ideas? Side to side. So it's essentially angle of yaw, right? And then we had angle of pitch, theta. What was this one?
Up and down.
Up and down, yeah. And then we had angle of roll, phi. This one was a little tricky, if you recall, because it accounted for the turning movement as well as the rolling movement, right? That's why we introduced the angle of bank, capital phi, which only accounted for the rolling movement, right, of the aircraft. We went over the coordinate system. We made a 3D thing that made everyone a little confused, which is the case with all the 3D systems. So this is the angles between XB, YB, ZB, and XE, YE, ZB, between these two systems. Then we define new angles that were going to give us the relationship between the air path axis, right, and the XE, YE, ZE. What was the first angle here? Was the azimuth angle. Or X, which is essentially the equivalent of angle of yaw, but in the air path axis system. The next axis was flight path angle. Again, the equivalent of angle of pitch, but in the air path axis system instead of the body axis system, right? And then we had the aerodynamic angle of roll, mu, which is equal to the angle of roll, but the air path axis system. Then we had two important angles that we introduced in the XYB XAYA system, and its relation or its angles with the XB, YB, ZB system, right? The body axis and the air path axis. What were those two angles? Angle of attack, angle of side slip, exactly. Angle of attack alpha, angle of side slip beta, which essentially talks about the angles your flight path, I want to say flight path takes with the body of the aircraft, right? Yes.
Could you go over quickly what's the difference between the angle of roll and the angle of bank?
So angle of roll, again, angle of roll takes, when you are rolling the aircraft, it is also turning, right? And this angle is going to be a little inclined compared to the coordinate system that is not turning, right? So that includes, that takes into account the angle of roll. So angle of bank is essentially the projection of angle of roll on the horizontal plane that doesn't turn. So your angle, let's say this plane is turning, right, and rolling. You are including both turn and the roll in the angle of roll. But angle of bank only includes the rolling of this plane. That's the difference. When it comes down to solving problems, you will probably be given an angle of roll or angle of bank. The equations of motions are going to be based on one of them. So as long as you're familiar with what things are, you should be fine. Okay, so, and we also talked about the components of velocity, right? Didn't we? That was the last thing we talked about. The components of velocity as well as the components of moments. The last thing we needed to talk about in the previous lecture that we didn't get to was the component of airspeed when a wind gust is present. So your aircraft is essentially moving in a windy condition, right? Your velocity, this pen doesn't work correct. Your velocity is going to be, let's call it V of G, is going to be your velocity vector of the aircraft plus the velocity vector of the wind, right? Let's say you have aircraft that is moving in this direction, and then you have wind gust in this direction. Your final velocity vector is going to look like this. Okay, what are the components of this velocity? I'm just going to write down the components for you. Of course, it really depends on the coordinate system you're using. If you are using the Earth coordinate system, the component of velocity is going to be V of xe, which is V cosine of the magnitude of velocity, V cosine of the flight path angle, cosine of the azimuth angle. In the y direction, it is going to be V cosine of the flight path angle, sine of the azimuth angle. And the z direction is going to be the sine of flight path angle. But if you look at it from the ground, in the xg, yg, zg, z of g system, these components will include the wind gust. So V from the ground, from an observer that is looking at the plane from the ground, is going to be V cosine of gamma cosine of x plus the wind velocity in the x direction. V cosine of gamma sine of x, the wind velocity in the y direction, and V sine of gamma, the wind velocity in the z direction. We are going to come back to this wind gust later when you have derived the equation of motion to find the equation of motions in the presence of wind gust, right? But for now, let's just keep it at the velocity components. So at this point, we are familiar with the components of velocity in general for different coordinate systems, of course, right? Because we have 4 different coordinate systems, which means that we can have 4 different or 12 completely different components of velocity, right? Also the moments, we understand the coordinate systems, we understand the angles, a lot of angles that are present, hopefully. Is there any confusions? About the angles.
So I think what was the U and the VX? G?
These are the components of wind gust. Is that what you are asking?
Yeah.
Yeah. I'm sorry, this is my mistake. All of these are W. Component of wind gust. W of W. That was my mistake. Okay, so the next logical step is, of course, to start talking about the equations of motions. But before talking about the equation of motion, we need to have a little bit of background about different types of flights and how the thermodynamic parameters change with altitude. Thermodynamic parameter variation. We usually assume that these are constant, right? We are not gonna do that anymore. I'm assuming, or I'm hoping, that you have gone over this in Aerospace 101. If your textbook was the Introduction to Flight textbook, this is going to be the chapter 3 of that textbook, this part of it. But we are going to go over it nonetheless, so that's no worries. It is a very simple thing to do. In my lecture note, I have also included the names of the different parts of an aircraft in case you don't remember it from your previous classes, because we have gone over it in the lab 1, and all of you have had the lab 1, right? Except for a couple of people, but they are in the lecture notes. So these are just names. Just go look at the names, right? Not very hard to understand. Let's just start with the type of flight. Types of flights. What are the different types of flights? Let's start from the takeoff. Takeoff itself is a type of motion during the flight that we have to understand, right? What's the distance needed to take off? You actually did your project for lab 1 based on this, right? You designed the plane and you were concerned. We didn't really measure anything, but the idea was that after a certain distance, it had to be able to take off, right, from the ground. And then we have the climb. So takeoff, climb, and what comes after climb? Cruise, of course. And what is after cruise?
Descent.
Descent, exactly. How do we write descent? One thing that happens a lot during descent is that you may need to hold at a certain altitude for the air traffic control to let you land, right? And then we have the approach and landing. So different stages of flight. And our goal in this course is to understand and study all of these different stages. We are going to start from a very complicated, or not complicated, very general equation of motion, and then simplify it for each case. We want to understand each case. As you can see, it is not that hard to simplify these cases, right? For cruise condition, what is the biggest simplification we have during cruise condition when you are studying the equation of motion?
Lift equals weight.
Lift, essentially velocity is supposed to be
Zero. Or constant.
not zero, constant, right? If it's zero, then you are in a very bad situation. You have to think of something, right? So this is the different stages of flight. Regular flight. But we can have another look at this. We can have different types of flight from another perspective. One of them is gliding flight. What is the definition of a gliding flight? Again, let me just clear everyone's mind before you jump in, that when you are talking about the equations of motions, we are talking about the application of the second law of Newton to the flight. So forces equals to the derivative of linear moment. So gliding flight. there is no thrust. Thrust is 0. Exactly. So when you are writing the equation of motion, when you are writing the forces that are applied on your airplane, thrust is going to be 0. Exactly. Next one, this one may be a little complicated. By non-side slipping flight. When we say that it is a non-side slipping, we are essentially saying that the angle of side slip is 0, right? What does this mean for our flight? What is the practical meaning of this for our flight? You guys just jump in. You don't need to take permission.
You're always flying in the direction of the wind. So
Yeah.
there's no change in that angle of the wind.
There is no crosswind, right? Essentially, there is no crosswind. Exactly. Crosswind velocity, 0. And hopefully if we go fast enough today, we'll get to the equations of motion for this specific type of flight. And then we have the straight flight. A straight flight. What is a straight flight? You have to speak up. I can't hear you.
Is that kind of commercial takeoff, flight, and then
Take off.
Body equals wind or air axis.
No angle of pitch. A straight flight essentially means that you are flying on a straight line. That's it, right? And the official definition, I have it actually here, which is the center of gravity of the airplane travels along a straight line, right? So all of these conditions, except for one of them, can be a straight flight, right? Except for this one. Except for the representation of this one that I've drawn here. In reality, that one also, some parts of it can be a straight flight. And the last one is the symmetric flight. Okay, what is a symmetric flight?
Equal time on takeoff, cruise, and descent.
No. Where is the symmetry there?
Or well, I mean, from the start to the midpoint is the same. Like you have an equal takeoff, I would say, compared to after the
No.
midpoint.
No.
Is it thrust equals drag, lift equals weight?
No. I mean, that can be a special case of symmetric. Yes.
is it equal lift and drag on both wings?
Equal lift and drag on both wings. Did you want to jump in?
I'll wait for him to finish.
I mean, that's it, right?
Wouldn't it be a flight in which both the angle of side slip is 0 and the plane of symmetry of the airplane is perpendicular to the horizontal plane of Earth?
Yes, that's it. That is the exact definition of it. And so if you have a top view of the plane, this essentially means that whatever is happening on this side of the plane is also happening on this side of the plane. You have a plane of symmetry on the plane, right? So as both Horton and John, right? John said, lift and drag on both sides are essentially the same, which means that the angle of side slip is 0, angle of bang, a lot of things are 0. And it's a regular flight that you have seen in your aerodynamics a lot. Right? We are flying at an angle of attack, calculate lift, right? This is essentially what you saw in your aerodynamics. And of course, aerodynamics can be can get more complicated, but you don't need to. You can always put the plane of symmetry on the plane and do some calculations. Okay, so with these out of the way, we can start talking about the forces on the plane, and then we'll talk about the changes of thermodynamic parameters. Then we'll move on to equations of motions. What are the forces applied on an airplane? I guess you have heard this question. You should have heard this question 4 to 5 times by now, right? So what are the forces?
Just lift,
Just jump in, guys.
just lift, drag, weight, and press.
These are the 4 main forces that we deal with, right? 4 main forces. But if you recall from your aerodynamics, we also have a normal and an axial force, right? In this book that we are dealing with, this actual book is shown with T, which is not a very good way of representing forces, because you may confuse this with the thrust force. So we're going to keep using normal and axial. What was the difference between the normal and axial force and the other 4 forces? Yes.
Normal and axial are component forces of like the drag and the lift forces.
They are related to lift and drag. So they actually both of them come from different perspectives on the force balance. If you write your forces on the body axis system, so along the chord length of the plane, right? Then you are going to deal with normal and axial force instead of lift and drag. So you are going to deal with normal, axial, weight, and thrust, right? Body axis system. If you do the air path axis system, you are going to deal with lift, drag, and weight. And the relationship between them was also given to you in aerodynamics, between the lift and between these two. The relationship between the 4 is called the equation of motion that we are going to see later, right? It's n cosine of angle of attack minus a sine of angle of attack. And drag is n sine of angle of attack plus a cosine of angle of attack. Now we can actually rewrite the equation the other way. We can relate normal we can find the normal and axial force based on the lift and drag. We can also combine lift and drag into an R force called the resultant force. Okay, and I'm assuming you have seen this before. What our book here has done, and we are going to see this later, adds this to your weight force and comes up with a force. Let's come back to this later. Let's just keep it simple. So types of flights and the forces acting on the plane. Next step is the changes of thermodynamic properties. Thermodynamic properties variation. Let's call them variations. The idea here is that as you change the elevation, your temperature changes. All right. This is something that we have 2 people who have taken fluid mechanics, right? Who were the 2 people? Fluid mechanics, mechanical engineering people. Doesn't have any mechanical. Yes, one mechanical engineering. The other one is writing. Right? Okay. You did talk about the changes with temperature and atmosphere in and elevation, right?
A little bit, yeah.
A little bit. And the rest of you talked about these changes with elevation in your what's it called? In your 101 class. Hopefully that is true. Essentially, we are mostly concerned with the changes of temperature with elevation. How does it change with elevation? Of course, we have different layers of atmosphere. We have some layers in which temperature change with elevation. So this is temperature. This is your elevation. This is your altitude. And we just say that altitude in kilometers. We start from an elevation. Your temperature decreases as you go up until you reach the boundaries of the first layer of the atmosphere, right? What happens next? Does anyone remember? It stays constant. So we are going to have an isothermal layer. Then it increases a little bit until you get to the fourth layer. It stays constant again. And again and again. So this happens. So to find the temperature at a certain altitude, since we are assuming linear changes all over or no changes at all, we can just find the equation of these lines and we should be able to find the temperature at a certain elevation, right? So how does this equation look like? The equation itself, that's how we write the equation. This is written in different formats. So you just have to be mindful. This is going to be the slope of your line. In case your temperature is changing, right? These cases. This slope is always going to be given to you. This is your target altitude. Let's say I tell you that I give you the temperature at altitude, whatever, 1 kilometer, and ask you to find the temperature at altitude 10 kilometers, right? This is going to be your initial altitude, that 1 kilometer. And the same is true for temperature, initial and target. So this is something that is given to us, that is always given to us. We have these tables that actually are based on these. Have you seen the atmospheric tables? Yes. And I'm going to put a PDF of all of the atmospheric tables on Blackboard, actually, in case you don't have them. Is there anyone who is not familiar with the atmospheric tables? Okay, that's good. So we are all familiar. Which essentially, you can find your properties at a certain altitude. So based on this, you can start from the ground, altitude 0, and start from the room temperature and all of the room properties, 25 degrees Celsius, and build up your properties at each altitude, right? And we have this type of calling the system that is tell you a pressure. They may, instead of telling you a pressure or property, they may tell you that this airplane is flying at this standard altitude. When they tell you that they are flying at this standard altitude, it means that you have to go to the standard atmospheric tables, look at that altitude, and read the properties off of it, right? Are we familiar with this? Okay. So that's it. That's essentially it. When you want to, we are going to use the tables. I have the equations and the lecture notes, but we are going to use the tables. You don't have to use any of the equations. Maybe for velocity, maybe for temperature calculations, just to make sure that you are clear on how, I guess, linear algebra works, right? You remember how it works. Maybe one homework question. Let me ask you one question though. Let's say I give you the temperature here, T1, I ask you to find the temperature here at this altitude using the equation, not the tables. How would you go about this?
Break it up into 3 sections.
You divide it up. One of you can start.
You just divide it up into sections.
That's it. So you essentially take the altitude here, find the temperature here. Temperature is going to be the same throughout. You are going to use this as the second H1 and T1. Find the temperature here. Temperature here is going to be constant, right? And then you start this one as a base altitude and go to this altitude, find your temperature there. Okay, it is good. So you still remember your standard atmospheric thing. So, if there is no question, let's start talking about the, yes.
We'd be given like where the layer, like we wouldn't have to
Memorize
memorize.
the,
Like the sections, like
the
all
slopes.
around, they'd be given like where the stuff. Where it's
Yeah, this is,
constant temperature.
you are not gonna do any like calculations because the standard atmospheric, we have the tables to relieve you of calculations, right? So it is a little, I guess, redundant work to go back and do these calculations. So everything will be given to you. Just one homework question, maybe, and that's a huge maybe. So let's just start with the equation of motion. This is essentially the meat of fluid mechanics. Interesting reaction. But equations of motion. We have two types of motion here, right? What are the two types of motion? We can rotate along an axis, and we can have an accelerating motion, right? So when we can rotate along an axis, what kind of an equation describes that motion? What kind of equation should we use to explain that motion? We know what we use to describe an accelerating linear or curvilinear motion, right? What is the equation?
F equals ma.
Newton's second law, right? Which for our case tells us sigma F is equal to the changes in linear momentum, right? This is what we saw in the review part of the class. So this is going to explain the curvilinear accelerating motion. What about the rotating motion? What comes into play in a rotating motion that this equation does not see? The moment of inertia. What else? What is the force component of it?
F equals I omega squared.
The moment, right? Moment. And what equation did we have for the moment? We just saw this equation in the review, the dynamics review, right?
MR squared. Or MR.
Sigma m, it is analogous to this. What was the equation that was analogous to this? All of the moments combine each other, or moments are always combine each other. So moments around the center of gravity is equals to changes in angular momentum with respect to time. Right, this is what we saw. This is something that we have seen in this course actually a couple of weeks ago, 2 weeks ago, right? And angular momentum is usually shown with H, but this book, our textbook, uses B for whatever reason. So angular momentum, H of CG is equals to B of C. These are the same thing, not equal, they are the same thing. Angular momentum. So moments on a body are equal to changes of angular momentum with respect to time, and the forces on a body is equal to the changes of linear momentum with respect to time. Any questions? No. So this is going to be the basis of finding the equations of motion for an aircraft, the most general equation of motion for an aircraft. Again, so, and also let's go back to the forces. The forces here are the resultant force, thrust, and weight. And then we combine these two. I think I said we combine resultant force and weight, but we combine the resultant force and thrust to get this A force, right? So whenever you saw A, it is just a combination of the resultant force and thrust force. There's nothing special, right? It is not a new force. Okay. And I have the derivations for the equation of motion in the lecture notes. And let's actually have them as a bonus point. So go back to the lecture notes. Start from this and this. Write down all of the components of velocities and everything, right? So your answer should be a little more expanded than what is included in the lecture notes, right? A little more expanded. And I guess derive the equations of motion. All of it. There are going to be 6 equations. Is this true? How many equations are we going to have at the end of the day? Is it 3 or 6 or 2?
6.
Why 6?
X, Y, Z, and the rotationals.
Exactly. We have X, Y, Z, and also the rotational. That's it. We're going to have 6 total equations at the end of the day. And we are going to use for this part of the equation of motion, we are going to use the body axis system to show our components. So which angles are we using when we are using the body axis system? What are the angles we use for the body axis system? We had 4 systems, right? The angles were the relationship between, we had like body axis system versus the moving earth system, and air path system versus the moving air system. Angle of roll, exactly. So for this part of the thing, we are going to use the angle of roll, let's start angle of yaw, angle of pitch, and angle of roll, or angle of bank, right, to make things simpler. Okay. So the equations are derived for the body axis system, and we are going to have the same equations for the earth axis, for the air path system. Make sure not to confuse this. These are both true. The force equations are going to look like this. A component of weight in the x direction. So this is the x of b in the direction of x of b. The component of weight plus the component of A force is equals to your mass, which is shown in your book, is shown by capital M. This is not moment, this is mass, right? Moment is shown with M of CG. Do we read the book? Let me ask you this. Is there anyone in class who reads the book? One person. So, pardon me? Okay, no. I just want to make sure that I keep explaining this. So if you read the book, you don't get confused.
Is this the aircraft performance one?
Element of aircraft performance, right?
I just want to make sure, is that like a minus W or is that like a?
Minus. Yeah, it is in the other direction. That is correct. This is not an equation. It just tells you that I'm writing the equation for this direction, for this axis. So minus W sine of theta, mass multiplied by the changes of u with respect to time is a component of velocity in that direction, plus WQ minus VR. What were Q and R? And why do we have this term? I mean, if you do a bonus point, you will figure this out, but I just want to make sure those of you who are not going to do the bonus point are also clear. What are Q and R? How did we define components of velocity are W and V, right? Velocity is UI. What is that?
So is it like the relative position vector and
No, it is not a position vector. Components of the angular velocity, right? Right? Components of angular velocity. Exactly. Thank you. So what were these components? P. Is it what were the components? Which component was in the x direction? Pi, Q, Qj, and Rk. So why do we have this term here? This is because dv dt, we have assumed m is constant, we have taken it out of the derivative. And this is because dv dt, the velocity and magnitude is changing, but its orientation is also changing. So if you recall, we said it's going to be dv relative dt plus omega cross product of v. So this is essentially the x component of that cross product. Okay? So don't be confused. So the next part, the y direction. We are going to have w cosine of theta sine of phi plus a in the y direction equals to m dv dt plus ur minus wp. The z direction, we are going to get w cosine of theta cosine of phi plus az equals to m dw, and this w, this is the small w, just make sure that you're clear. A lot of similar notation. So whenever you're taking the derivative of a w with respect to time, we are talking about the component of velocity in the k direction. And it's very hard for me to show. Let's make it capital W, like this, to distinguish weight from the component of velocity. And then the rest of it is going to be Vp minus UQ. Bless you. So, we have three separate equations for force. Moment equations are arguably more complicated. This is just a simple force balance, right? I mean, a little more complicated. So moment equations for the x direction, again, x of b, we are going to have this. M in the x direction. And this is the moment, right? Just a singular m refers to mass in your book. M with a subscript refers to moment. So it is going to be equal to dp dt I of x. What is I of x?
The moment of inertia about the x-axis.
That's it. Moment of inertia about the x-axis, right? Plus dq dt I of xy. And I assume you understand what I of xy is. And dr dt I of xz. Plus q bz minus r by. M of y, which is in the y of b direction, is equals to dq dt. Or let me actually make sure it is going to be, let's start with dp dt I of yx plus dq dt I of y plus dr dt I of yz plus r bx minus pbz. Right, yes. Z of b, m of z is equals to dp dt. This time is going to be I of zx, dq dt, I of zy, dr dt I of z plus pby minus qbx. So 6 equations. These equations govern your flight. whatever type of flight you have, you can find based on these 6 equations.
So if you're writing those,
You can.
it's a problem.
Yes, deriving these 6. I mean, we can actually write them in vector format. And vector format is, of course, I mean, we already have them in vector format, so let's just forget about it. This is the vector format, right? So you want to start from the vector format, get to this. Again, this B is talking about angular momentum, and this is how your book, this book, the problem is we use a couple of different books for this course, and all of them have their own nomenclature, which happens. Make sure you are not confused.
So B is H also in this case?
Pardon me?
B is the angular momentum?
B is the angular momentum, yes. In this case, yeah. Okay. What time is it? We went past enough. That's good. Okay, so we have this main equation, but I mean at this point in your education, you already know we never use the big equations, right? Because there's always something you can do to simplify the problem. And as we saw for different types of flights, they are mainly very simple cases, right? That we have to deal with. We are going to talk about a little more complicated cases as well later. But most important flights are very simple. Right? Just linear accelerated flights or unaccelerated flights. So let's try to simplify this. Let's start with a formulation for a general, a steady motion. What do you think this means? A general, a steady motion. Again, we are writing this equation for XB, YB, ZB, the body axis system. For this specific purpose, we are going to use the air path axis system as well, which is going to give us a simpler solution. So we are going to use that as well. So
Are you moving in a straight, are you just flying in a straight line?
but is that what a steady motion means to you? It's just a straight line?
Well, no, is that part of it? I was just saying.
No, just the assumption is it's a steady motion. That's it.
No acceleration sounds pretty steady to me.
No acceleration. Okay, that's fair. Does it mean there is no rotational speed as well? Not necessarily, right? Angular acceleration, yes. Maybe it is 0. But rotational speed, so we are still rotating, right? We may rotate. But it's not accelerating motion. So angular acceleration is essentially 0. So what can we say? We can say in these equations, what are things that are 0? All of the dt's, right? Not all of them, but most of the dt's. So du dt is equals to dv dt equals to dw dt equals to dp. Also the moments are 0, right? The changes in moments. dq dt and dr dt. All of these are 0. The changes in pitch, angle of pitch and angle of roll are also 0. Because it is going to contribute to angular acceleration. The only changes with respect to time that is not 0 is the angle of yaw, because we still can have rotation, and to rotation your angle, one of the angles must change, right, with rotation spin. So we are going to define omega as the changes of angle of yaw. Which is defined as the changes of angle of yaw. Okay, so let's rewrite the equation using this. The first three equations going to look like this: negative w sine of theta plus ax a of x is equals to m wq minus vr. W cosine of theta sine of phi plus ay is equals to m ur minus wp. Yes. And then we have w cosine of theta cosine of phi plus a of z is equals to m vp minus uq. We can have the same simplification for the m equation. I'm not going to write it down here. We're just going to focus on the forces, which essentially means that for the, if you write this for the m equation, these parts are all going to be 0, right? Okay. Any questions so far? The general steady motion. But what does this motion look like in the most general term? Of course, a straight motion of an aircraft is included in this, right? But it's a little simpler. What does this motion look like? Can we have any climb or descent?
No,
Why not?
because of acceleration.
It's accelerate climb.
If your velocity is already in the pitching, in the climbing direction, and it's not changing,
Yeah.
then you are not. The idea is you are not changing anything. If you are already in climbing position, you are going to climb, right? Are you going to rotate? I mean, there won't be any rolls, but are you going to rotate with very large radiuses, of course? Is it possible?
Yeah.
You have angular velocity, so rotation. So your general steady motion in the most general form is going to be a helicoidal. And how does this look like? You are essentially going to move up or down. I mean, this is a very bad drawing. The radius doesn't change. This is the most general form of it, right? You may say the angular velocity is 0. It is going to be only a straight flight, right? There won't be any rotation. Of course, this axis itself can move, right? So when you are looking at it from the body, it will look like you are just moving up. But from the earth, on the surface of the earth, it may go like this. Just keep that in mind. Okay, the most steady type of the aircraft. We can change our perspective and look at this equation of motion from the air path axis. And write the equation of motion with those. And then we can combine all of the moments together in one force. All of the rotations essentially in one force, which is the centrifugal force. I'm going to write the equation, and this is going to be the main equation we are going to refer to from now on, right? I'm going to write this equation, and I'm going to expand that A force into its components, drag, truss, and all of those things. And we will talk about that one. In the X, you are going to have the negative drag. Or let me ask you this. On the air path axis, what are the forces present in the x direction?
Drag and thrust.
Drag and thrust. Is it possible we can have a component of weight as well, right? Depending on the direction of the flight, right? So that's it, exactly. Drag minus T, and we are going to talk about this angles, cosine of alpha T plus cosine of beta minus W sine of gamma, the flight path angle. Okay, again we are in the air path system, so the angles are going to change to the air path system, of course. What about the y direction? What are the forces that can be present in the y direction?
Lift, drag? No.
No,
And wait.
because that's a very important actually. Who said lift and drag?
No, I mean, lift and weight.
Lift and weight. What is this true?
Thrust.
Lift and weight. Do we have lift and weight in the y direction?
Yeah.
Yes. No.
No.
Why not? Because this is not how we defined the y direction. You have to keep that in mind. Just have to be careful. XA was this direction. This was y in the side slip direction, right? I mean, later in one of your problems, you may define the y-axis as this axis that is pointing toward Earth, right? But this is not our standard of work. If you do this, if you just define this as y and give me the forces in y direction are like this, if you give me the correct forces, it really doesn't matter what do you base your frame of reference on, right? As long as you have the correct calculations. But when you're looking at the book, make sure you're not confused. Or when you're looking at the lecture notes or you're coming back to your notes, make sure you're not confused.
In
Okay.
this instance, we have some roll angle, don't we?
We may.
So wouldn't there be some lift component in the y?
I just wanted to make sure that you are clear that this is different from this. So the component of forces are going to be different. We are not going to show it as a lift force though. I'm going to tell you. We will have some force, which is essentially the lift component, that force, called the side slip force, negative of S in that direction. Okay, and then we can have thrust, which is cosine of alpha T sine of beta plus W, and this is weight here, W cosine of gamma sine of mu minus, and again I'm including the rotational things in the forces, so we are dealing with centrifugal force, not the angular velocity anymore. Cosine of mu, the aerodynamic angle of roll. So this is x of a, y of a, and then the z of a. What time is it? For the z of a, we are going to get lift. We may have thrust. We may have weight. And we're definitely going to have weight. Cosine of mu plus c sine of mu equals to force. What is the good thing about this perspective is that on the right hand side you always get 0, right? Which is going to make things a little less confusing. How do we calculate the centrifugal force? We have the equation from the previous lectures. This is W divided by G, V omega cosine of gamma, which can be also calculated using WG V squared R cosine squared of omega gamma, I'm sorry. Okay, and this force, the side slip force, is a force that is going to be a component, an extra component of the resultant force. So it is not necessarily the lift or drag, but it is going to be a separate component of the resultant force, right? This is essentially the projection of the resultant force in the y direction. Okay. Do we have any questions? This is going to be the main equation of motion for the general steady motion. You may have some rotate. It is essentially helicoidal flight, right? Is there anything that doesn't look familiar to you, or we didn't really explain?
Why is it alpha T?
That's yeah, exactly. That's what I wanted to. That's what I wanted one of the aerospace engineers in the room actually, to get to. Why do we have alpha T, not alpha?
Because it could be offset from the body.
What could be offset from the body?
The vector of the thruster blows.
The vector of the thrust. So if it was an offset from the body, you are saying that we should have had T cosine of alpha, right? The angle of attack. Is that what you're saying?
If it was in line with the body.
Exactly. That is true. So this alpha T comes from something called the thrust vectoring. Is there anyone in class who can tell me what the thrust vectoring is? Yes.
System on some aircraft where they can usually manipulate the exhaust to change the thrust without having to like move any of the aerodynamics.
Exactly. So to change the direction of the thrust, that is called. So essentially, you change the direction of exhaust to change the direction of the thrust force, right? That's actually you have your what is a very famous example of thrust vectoring? Aerial jump jet, or what else?
Yeah, 22.
F-22. Or maybe what is a specific type of flight?
VTOL?
Vertical, yeah, vertical. All of these are very good examples, right? So this comes from the thrust vectoring, and alpha T. Let me actually draw the. We have a specific drawing here, a lot of drawing. Alpha T is defined as alpha plus this eta angle, which is the thrust vector angle. And let's have a side view of the aircraft. Side view. Let's say we are looking at the aircraft from these sides. The idea was this was x of b, right? Let's say we are flying in this direction. This was x of a. This is going to be your angle of attack, alpha, I'm sorry. Just a regular alpha. If your propulsion device is at an angle, you are applying a thrust vectoring. And of course, if you are projecting this thrust force on this axis, you have to include both eta and alpha in your projection, right? So that's where alpha T comes from. So we are at this point, I'm hoping we understand all of the new components here. The S, the C, and the alpha T. Main equation of motion for the general steady flight, non-accelerating flight. Let's try to make this even. Let's try to actually simplify this for other types of flight, right? Let's start by, and this is a quiz. So just tear out the paper from your paper. I'll try to bring some paper for you guys next time that I'm giving a quiz. We want to simplify this. It is going to be quiz 3, right? 3. Just make sure to put a date on it. The quiz number is not as important as the date. A steady, straight, non-slipping motion. What will be the equation of motion for this one? It is a steady, a straight, non-slipping motion. Since it is one of the cases of a steady motion, you have to use these equations, right? These three equations. Because it is a non-accelerating flight, a steady flight, right? What are the cases here? What are the other assumptions? Or what are the other simplifications? It is a straight flight and non-slipping flight. What is going to be zero for a non-slipping straight flight? Or what can be? Beta is zero. The angle of side slip is zero. What else? S is going to be zero, right? S is there because of side slipping. Is there anything else we can take out? Angle of, what can you take out of this equation? Angle of what? Angle of what can we say about angle of roll actually? Is it zero or no?
Is it equal to the bank angle?
It is this analogous to the bank angle, right? That's where the angle of roll is also zero. That's true. That's true. I made it unnecessarily complicated. What else? A steady, straight, non-slipping flight. There is no roll. There is no yaw. So there is no S. There is no mu. There is no beta. Is there anything else we can take out? Any ideas? A steady, straight flight. It is a non-slipping flight. It is a steady, so there is no roll. When there is no roll and there is no yaw, what does it mean? It is moving on a straight line. What force is not present when you are moving on a straight line? Lift? No, lift is definitely present, right? We are on a straight line. What force contributes to a curved motion?
The centrifugal force?
Centrifugal force, exactly. So centrifugal force is also zero. Okay, so let's write the equation of motion. I guess I'm going to give you a little bit of time for the next one. This one, we are going to have D minus, of course, the forces in Y direction are all going to go out because there is no movement in the Y direction. We only have X and Z. So T cosine of alpha T minus W sine of gamma L minus T sine of alpha T plus W cosine of gamma, and this is the weight. So next case that I want you to get to, and whoever gives me a correct answer on this will get a bonus point, right? Then we will come back and I'll give you the answer during the next lecture. And when you're done with this, the class is essentially going to be done. So you can leave the room if you finish this. It is a steady straight side slipping, right? So we are going to have a side slipping motion. How would this equation look like? And please do not look at the lecture notes if you have them with you, because the point of it is for you to think and give me the correct answer. Of course, the wrong answer is not going to be penalized. It's just a bonus point.
Can we look just to remember what angles are what?
What angles? What
What angles are what Greek letter?
What angles are what? Okay, let's talk about it. What angles do we have here? What is the azimuth angle? We had azimuth angle, right? That's x. What was the other one? What is the aerodynamic angle of roll? Mu. What else did we have here? The flight path angle. What is that one? Gamma. What is the angle of side slip? Beta. What is the angle of attack? Alpha. But here we deal with the angle of attack plus the truss vectoring, alpha of t.
How is this different than the general form of the steady state?
That's what we want to figure out, right? It is, I guess we are done. It is 11:20, so let's just work on it for like 2 minutes. And we are going to give this class to the next class. It is a steady, straight, side-stepping motion. What is the difference between this one and the general steady motion?
So we can roll. Or turn, I should say.
It can turn. We have one vote for it can turn.
So when we're defining straight, is it just like in like the horizontal direction, or like is there no gamma, or would you still consider like if there's a constant flight path angle?
That's a straight. As long as it is a straight line, right? Should be fine. Okay, so is 11:22, 11:20. It is already past the class time. If you are done, you're done. You get the bonus point. If not, you'll get the attendance point, which is also equally important. Thank you. Make sure to submit your quizzes. I will give you the quiz back on Tuesday. Your homework 3 is going to be posted today. Make sure to go over it during the weekend. Thank you. And have a good weekend. Enjoy your